Hi all, welcome to Geeks for Geeks. Let's talk about challenge 143 coding questions. So here the first question is magic array. Let's understand the question first. Here we are given an array where we have to check array is a magic array or not. So what the meaning of magic array here? An array is said to be magic array if no two consecutive integers in the array have same parity, right? If it's a magic array, we have to return 1, else we have to return 0, right? So in this example, we have four integers 1, 2, 3, 4. Its output is 1. So here, what we are seeing in the explanation, their first pair is 1, 2, right? Second is 2, 3, and third is 3, 4. All the pairs having sum equals to odd, right? It means that all are odd, we have to return 0. In this case, 1, 2, 4, 3. First pair is 1, 2, its sum is odd, right? And second pair is 2, 4, its sum is even, right? We have to return 0 in this case because 2, 4 is a parity, right? But we have to find non-parity, right? All the pairs should be non-parity. So let's understand a bit of this question. So let's divide parity and non-parity. Here the definition of parity. If they have same property, two integers having same property, right, and divisible by 2, it's a same parity. So for example, we have two numbers 2 and 6, right? In the example 2 and 6, they're having a same parity, right? Same parity means both are even, right? And while 3 and 7 have same parity because they both are odd. 3 and 7 they have odd, right? It having same parity. So let's talk about non-parity. Non-parity simply tell us that the pair should be odd even or even odd. It should be even odd or odd even, right? So how to find this question? How to solve this question? In simple words, in a parity, right? In a parity part, if we add both values now, even plus odd, right? Its sum will always, for example, let's take 2 plus 3. Its sum is always odd number. Sum is always a odd number for non-parity case. But in parity case, if we add even plus even number or odd plus odd number, its sum is always even number. Let's hear 2 plus 6 is 8, 3 plus 7 is 10. As you see, its sum for both the cases is even. Both is even. So here the intuition to solve this question is we have to run the loop. Let's dry run. We have to run a loop. For example, in this question we are given 1, 2, 3, 4. Or let's take this 1, 2, 4, 3. 1, 2, 4, 3. Right? So the first pair is 1 and 2. It's odd. It means it's a non-parity case. What we want? Second is 2, 4. It's even. It's even, right? It means that it's a parity part. But we want our all the pairs in the given array should follow a non-parity case. So here this is parity. So we have to return false in this case. Return false in this case. The simple intuition is we have to take two numbers. If its sum is even, it means we have to return false in this case. So let's code this. Here the sum of two integers is array I plus array I plus 1. If sum divisible by 2 equals to 0, in this case we have to return false, else If it's pass all the cases, we have to return true, right? Let's submit this. Okay, compilation is good. Now let's submit. Yeah, problem solved successfully, as you see. Let's talk about now second question. So second question is not a palindrome string. So let's understand the question. Given an palindrome string is of length n, Geek has to replace a character in the string such that resultant string is not a palindrome, right? And also we have to return that non-palindrome string in the form of lexicographic smaller string of s. If no such string is possible, we have to return -1 as a string, right? So let's understand this question. So CABBAC will be given as example. Let's take this example. So our string is CABBAC. If you clearly see, this is a string. This is a string and it's a palindrome, right? Let's make an array of it. CABBAC. So if you see, divide this string into two halves. So all the characters like C is matching with the last character and second from first start and second from the last is matching. This is also matching. So how to approach this question? It's very simple. It's very simple. We have to, our task is we have to make non-palindromic string and non-palindromic string. Second is return lexicographic smallest. Lexio smallest, right? This is the two tasks which we have to solve. So intuition is very simple. We have to traverse our first half of the given string, and if we encountered with any non a character, we have to replace with a, right? For example, let's take a same example. So we have to check only the first half, right? So here the first element is C, right? And we know that it's a palindrome. We have to convert it into non-palindrome. So if I change this to A, the very first non-A character we have to replace with A. It, see, now it's a palindrome or not? It's not. It's not. And it's not a palindrome. The second step we are also fixed. It's a lexicographic smallest. How? Because we are changing from start, right? We are changing the starting character, non-A character with replace with A. So it make AAB BAC, right? So here we can solve this. This is the approach to solve this question. So let's take example. If S is a single character, A, B or any C, single character is always a palindromic. Can we replace it and make a non-palindromic? Just think it. We cannot. We cannot. So this is a second part of it. Second approach, second thing which we have to keep in mind. If n equals to 1, we have to return -1 in this case. We cannot make this string as a non-palindromic part, right? So let's take example third part. Let's make a string as AAAA, right? So approach is similar. We have to divide this string into two halves and check that in the first half can be encountered with any non-A character. Let's see. This is A, this is A, this is A, and this is also A, right? And we are dividing this into two halves and check. First is A, second is also A, and we are not encountered with any non-character, any non-A, right? We are encountered with only A's. So how to change that string into a palindromic? How to change? And also the second step is lexicographic smallest. Okay, lexicographic, we have to make it lexicographic smallest string. How we can make? After A, we have B, which can make a lexicographic smallest, right? But where we have to replace? If we replace, there are four, length of 4. So let's replace it first. B, A, A, A. Second, we can replace at second position. Let's make it at second position. Now let's replace at third position. Now the last, we can replace at the last position. So if you clearly see, all the four strings are converted into a non-palindromic string, right? But first task is completed, right? So we have to also see, we have to also return lexicographic smallest, right? How we can do this? We have to choose between these four string which is smallest. Just visualize. I think the last one is the smallest, right? Last one is the smallest. So the here the intuition is, if there is no non A character in first half of given string, then in that case we have to replace our last character of string with B. Last character with B, right? This we have to keep in mind. Hope you understand the intuition. Let's solve this now. So the first is the base case. If the length of the given string is 1, we have to return -1 in that case, right? Else we have to check it the first half of it. In the first half, if we encountered with any non A character, our task is just to replace with A and return that string, right? But if we don't have any non-A character in the first half, then we have to replace the last with B. And now we have to return, right? So let's check this code. Yeah, let's submit it now. Yeah, it's correct. Let's talk about now third question. So our third question is equalize the distribution. So let's read the question first. Geek loves collecting candies and he has n different kind of candies in the collection defined by an array, right? So we want to distribute candies among some childrens and each child should get equal number of candies of all the types. Of all the types, determine minimum number of candies to be added such that all children can get equal number of candies. There can be any number of children, but it should be greater than one, right? But all candies must distribute equally. Determine the minimum number of candies to be added at each index, right? So here the first example is we have n number of n types and we have this array tell us that number of candies in all the different types, right? And here the output is 2. So let's understand the question. Let's take the similar example. So we have n type, n equals to 5. We have 5 different types, and in this type we have 3, 4, 5, and 6. Let's understand first, like in the question said, we have n different types of candies, right? N different types. It means that this is of different type, 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 this is of different type. You can take it like this is the candy, right? This is a toffee, right? You can differentiate like that, right? And number of candies we have 2, number of candies of type 1 is 3, number of candies of type 2 is 4, number of candies of type 3 is 5, number of candies 4 have 6, right? So we can differentiate like that. Now, question said, question said, we have to, we have to distribute among children's, we have to distribute the candies among children's equally of all type. Just note this thing, of all type. We have to distribute all different types of candies equally to all the children, right? And second thing, the question say more than one child, right? We have to distribute among more than one child. It means that children should be two or more, right? Two or more. And we have to return minimum number of candies we required to distribute among more than two child, right? More than two child. How to solve this question? How to solve this question? So first of all, let's talk about children first. Let's talk about children first. Here the minimum children we can take is 2, in which we have to divide the n type of candies equally. What will be the minimum is this? Minimum we can take 2, right? How much we can take? Maximum children we can take. How to find this? Suppose it's very simple. We can maximum children we can take is maximum number of candies in the given array. Like for example, we have 6 as the maximum number of candies of type 4, right? Let's take maximum children 6. Now I explain why it's 6. Because we have to divide equally to all the children's, right? Suppose we have 6 candies in the 4 type. Fourth type we have 6 candies. The condition tells us that we have to divide equal number of children. If we take 6 children, we can divide into one candy to each child. We can divide one candy to each child, right? Right? Each child can get one candy. Can we take seven children? Just think about it. Just think about it. Can we take seven children? Like we can give one child one candy, one candy, one candy, one candy, one candy, and one candy. We have seven children, but candies are six, right? We don't have any more candy left to the which we can give to seventh child. It means that it's clearly understand from this line the maximum children's range is equals to 2 to children array max value, right? Array's maximum value, right? So I hope you understand this part. Let's talk about further intuition. Let's make again 2, 3, 4, 5, 6. Okay. So how to solve? So here we can understand that our children should from 2, 3, 4, 5, 6. And we want minimum number of candies, right? We want minimum number of candies we need to split into the equal part to any child, right? So here are 5 cases. Let's make our answer, let's store our answer, which tell us that maximum infinite candies we need, but we need minimum. We update later on. So let's take in first case we have children we have two, in which we are distribute all the given candies to it, right? So here children is 2, right? So let make a column type, and here I write candies. So zeroth type we have two candies, and in this case we have two children, right? We have two children. Let's make C1 and C2. We have two candies. We can easily split into two child. I can give one candy to that child and one to that. So here we needed zero candies, right? How to solve this case? Simply, uh, if candies modulo with children equals zero now, it means we don't need it. We can easily divide into equal parts. In this case, we have to return zero, right? So let's take type 1. Here the type 1 is number of candies we have 3. So we can give 2 to this, 1 to this. But this is not in a equal distribution, right? So in this case, how many candies we left? If we give 1 to this and 1 to this, equal number of candies, how many candies we left? Let's write down here. Candies left, which is if we modulo candies with child now, we can get it. We can get it. This is 1. Here candies are 3 and our children are 2. It will give 1. One candy is left, right? So we have one candy. Now, how many children are left? Like for example, if I give remaining candy to C1, right? And it will make 2 to this part. How many children are left which don't have equal candies, right? How many children we left? One children we left. How to calculate? So here we have to calculate children's left, right? How many children's remaining or left? It's simply total children minus candies left. candies left. So here children are 2, right? Candies left is 1. It means that one children is left. If we need one more candy, right? If we take one more candy, we can split into equal halves, right? We can do equal parts. So we need one candy, so we can take from this. We need this type of candy one more, so that we can give to this C2 also, right? Now type 2, we have 4 candies. Go to this part. Candies are 4, children is 2. We can equally split into it. So here we don't need anything. We give 2 to this, 2 to this, and we need 0 from outside. Now type 3 have 5 candies, right? Check here. We give 2 to this part, C1, 2 to this. We are remaining with, here we are remaining with 1, right? We are remaining with 1 and child is also 1 left. Let's suppose we give 1 to this, right? Candies left is 1, but the children also left 1. So children minus candies left, which is 1. So we take 1 from this. Only then we can equally split. So here 3, here 3. Now we go to type 4 and candies are 6. We can equally split 3, 3. We can go from here, right? We return 0. We don't need any candy more, right? Now after that, we add all the candies, right? We all which we need. If we have children too. So what's the count here? 0 plus 1 plus 0 plus 1 plus 0, which is 2. So it means that for children 2, we need 2 candies. If we want to split n candies into a equal distribution. Let's take a dry run when we have children 3. So let's make this array again here, so you can easily visualize 2, 3, 4, 5, 6, right? And we are also storing our answer as 2 here, right? Let's do for child 3. Now we have child 3, same we have to do it again. We have 3 children. Here we have the type part, candies, here C1, C2, C3. Now 0 type has 2 candies, so 1 we give to C1, 1 to C2. Now C3 are left with, how many candies we are left with? We are left with, it's 2 and our children is 3. Our children is 3. Let's make it 3. So our candies left is 2, right? And our children is 3. Let's make it 3 minus 2, which is 1. So we need 1, our one child is left. Okay. So one child is left. Let's take from here. I hope you understand this intuition previously. So let's make it. So type 1 has 3 candies. We can give easily and we need 0 in this case. Now type 2 has 4 candies. We can give 1 to this, 1 to this, 1 to this and 1 to this. We need 2 more candies so that it will be equally distributed, right? We need 2 more candies in this case. So let's take 2. So type 3 has 5 candies. We give 2 to this, 2 to this, 1 to this, right? We need 1 more candy. So let's add 1 into it. Now type 4 has 6 candies. So we can easily give 2 to 3 children, right? So we need 0 candies here. In this case, we need 4 candies. 4 candies. Can we replace our answer? Can we replace our answer? No, because we need minimum number of candies needed. So same process we have to do for, we have to calculate for children 3, 4, sorry, 3 we already count, 4, 5 and 6. And if any one can get minimum number of candies, we have to update that and return that candies in terms of here answer, right? This is whole intuition. Let's solve this question now. So here, first of all, we have to find the maximum number of candies in our given array. Let's make its max as 0 and update the max, right? So this is the limit of children's, right? It started from, as I said, 2 is the minimum child we have to split up to max, right? Let's make it a child. It's a children, okay. So I represent children's. Here we have 2 children's and go for the max of it. Now we have to count it or say as candies we needed. Candies are 0. Now we have to traverse whole array, right? Now we have to add the candies and check with the helper function. We have to pass 2 things. First is candies, right? First is child. Child is I and second is candies. It means we have to pass array of j here, right? Now let's make a helper function which tell us that, or say let's make it candies required. Let's make more readable, candies required, right? Yeah, it's okay. So first parameter is children and second is candies. Now same steps we have to write here, right? If candies modulo children equals to 0, we have to return 0 in this case, right? We have to return 0 in this case. Now how many candies we are left? Candies left. So it's simple, candies modulo children, right? Now how many children are left? So children left is total children minus candies left, right? That children's we have to give. It tells us that how many children we left. It means that how many candies we are required to make it equal distribution, right? Now we have to update our answer in all the cases, and which has the minimum value we have to return, right? At the end we just have to return the answer part. Let's read once. Here we have find the maximum child from the given an array and its range is 2 to max. Now the candies are 0, right? So candies plus equal to candies required. Ij we are passing here the candies required children's candies, right? So if the candies modulo child equal to 0, we return 0. Here the candies left is candies modulo children. Now the children's left is children's minus candies left and we have to return. Let's compile it. Okay, so here we have to write the answer which is int max. Now let's submit. Let's compile first. Yeah, let's submit it now. Yeah, it's all test cases are passed. Let's talk about time complexity of this. Uh, we are going n time, right? We are traversing whole array, right? So it's in this case the complexity is big of n. Now for this looping part. So the maximum value in the array now, maximum value in the array is 10 raised to power 3 as you see the constraint part, right? So it's a constant, or we can also replace this with the 1000 part, right? So it's a constant loop, and inner loop is goes to n, right? So this is constant, this is big of n, and this is constant, right? And this is also n, right? And this is also constant, right? This is also constant. So we can write here constant, right? So overall time complexity is big of n plus big of n, which is equal to big of n, right? Hope you understand this question. Let's talk about next problem. So our problem name is optimize shuffling, right? So let's understand the problem first. We are given a tree having n nodes and given a 2D array edges, right? Which represent the edge of t, right? At the onset, every node holds a value which is equivalent to its node number. You have to redistribute these values across the nodes such that no node retain its original value. So we our task is to first task. There are two tasks. The first is we have to find the minimal aggregate, right, distance between its initial and the final position of all the nodes, which tells us minimal means mi, which denotes mi. Second task, the maximum aggregate distance between initial and the final position of all the nodes, which denotes ma. So we have to return that pair of mi and ma, right? So let's see its example. So here the example is we have given a n as 4. We have 4 nodes, right? And their edges, first edge is between 1 and 2. Second is 3, 2 to 3 and 3 to 4, right? So the output is 4 as a minimal distance, right? And 8 as the maximum distance. So let's understand this case first. So we have n equals to 4, which tell us that we have 4 nodes, right? Let's make the edges of it. So first edge is 1 to 2, right? Second is 3 to 4, sorry, 2 to 3, and then is 3 to 4. Now the first task is find minimal distance. Minimal distance. Second is find maximal distance, right? So what the question say, we have 1 2 3 4, right? So it's onset means here the line said at the onset every node holds a value equivalent to the node number. It means that node number is 1, so its value they have is 1. Node is 2, so its value is 2, right? Here the node is 3, so its value is 3. 4, here value is 4. So let's understand the what we want. You have to redistribute these value across the nodes such that no node retain its original value. What the question say, right? It's a one now. It's a one which is the initial position. It's an initial position, right? We have to change. We have to shuffle this one value, right? At any other node, 2, 3, 4, right? Let's suppose one is at this place. Okay, one is at this place. If one is at this place, 4 will goes to this place, right? Right? It's a final position. It's a final position. Okay. Black color, it's an initial position. Now, 2 at this place, right? Let's make 2 at this place, final position. 3 at this place, right? Just we are just swapping with each other. So the question said find the minimal distance if initial position is not at its correct position. We have to change it. So we are changing it. It's initial position. It's a final position now. Final position is 1 is going to fourth node, right? Fourth node. It's a final position of 1. Now, so we have to find the minimal. Let's suppose now 1 is at this place, right? So now 1 is final position is this at 4. How many distance, how many edges are in between its final and initial position? We have to count that. So as you see, initial position of 1 is this and final is this. How many edges in between these final and initial position? First 1 edge, this is 2 edge, this is 3 edge. It means 3 edges are there. For 1 it's 3 edges. So it means the distance between its initial and final is 3, right? Now let's talk about 2. 2 is at this place, its final position is this. So how many edges are there? Only 1. So for 2 have 1. Let's talk about 3. 3 is at node 2. So edges is 1. So let's add 1. Now 4. 4 is at 1st node. So how many edges are there? 3. So let's add 3. So this is for 3 node. This is for 4th node. What's the count is? It's 8. It's 8. Let's suppose let's check for this. If we are right, written the final position at this place. Let's suppose initial is 1, 2, 3 and 4, right? Now if we make, if we change its adjacent node values, for example 1 is at this place. So what is the nearest node to 1? Just think, because we need the minimum, right? We need the minimum. Which is the minimum node which is present to 1? It's 2, right? So just change with it now. Just change with it. Final position of 1 is at just just adjacent node. So 2 is going to this place, 3 is going to this place and 4 is going to this place. Let's check its distance now. So for 1, how many edges between initial and final, right? Only 1. So for 1 is 1. Let's talk about 2. 2 initial position is this, final is this. How many edges in between? 1. Let's write 1. For 3, let's talk about 3 now. 3 initial position is this, final is this. How many edges? It's 1 now. So just write 1. For 4, its initial is this, final is this. How many edges in between? 1. So just add 1 plus 1 plus 1 plus 1, which is equal to 4, right? Which is equal to 4. If we compare these two things, 4 is the minimal, right? 4 is the minimal. So what's the intuition to solve the minimum distance? Just replace with its adjacent node, right? Adjacent node. So let's talk about how to find. I hope you understand how to find the minimal, right? Minimal distance. Now let's talk about how to find the maximal part. right? Let's suppose 2, 3, 4, right? Now we want maximal, right? We want maximal. So initial value is this, right? Initial value is this. We have to write 1 at the farthest distance from the initial position. What is the farthest distance? I hope this is the farthest. Let's write here. Let's write here. Now, for 2, which is the farthest? It's 3 because 4 is already occupied, right? 4 is already occupied. If 4, we have to swap, so 4 will become here, right? So for 2, farthest is 3, right? So we have to swap with 3 part. So 2 is here, 3 is here. Already we are sorted. We are already worked on 3 and 4 node. Now let's find the distance. So the distance is, one initial position is this and final is this. How many edges are there? 3 edges is there. Let's talk about 2. 2 initial is this, final is this. So how many edges? 1 edges. Now we are at 3, right? So how many edges is in between its final and initial position? 1 edge. So just write 1. For 4, how many edges are there? 1, 2, 3 between its initial and final. So write 3. So its maximal distance is 8. So our output is 4 and 8, right? 4 and 8 is our output, right? I hope you understand. So what's the intuition? For minimal part, first we just replace or say swap. We just swap with its adjacent nodes, right? And for maximal, we swap with farthest node, which is at max distance from the initial position, right? So these are the 2 points which we have to keep in mind. Now let's see how it's working, right? Let's do step by step how the code is working for it, right? So first step is we have to create a adjacency list. I name it as a graph, right? Having n values, it's n having the n size, right? Now we are just make the adjacency list here, right? Now when the adjacency list is make, we are just making a variable, right? We are just making a array with n size where I put the initial value into it. Let's write the first write the make a adjacency list. Let's make it. So we have 1, 2, 3, 4. Let's make it, and n is 4, right? So let's make it into a 0 indexing part. So 0, 1 becomes 0, and this is 1, this is 2, this is 3, right? Now let's make it. We have adjacency of n size, means 4 size, 0, 1, 2 and 3, right? So 0 is with the 1, its adjacency is 1. For making a 1, it's 0 and 2, right? For 2, it's 1 and 3, right? For 3, only 2 is there, so it's the adjacency part, right? Hope you understand this, right? Now we want to change the shuffling. We have to change the shuffling. So initial position, let's make an array of n size, right? let's name it as A, and its value, so this is the 0 node, right? Its value is also at 0, 1, 2, 3, as I tell you before. So here we are adding at 0 node, we have 0 value. At 1, we have 1 value. At 2, we have 2 value. At 3 node, we have 3. So this is the two-step conditions, right? So adjacency list is over, right? We make the adjacency list and we make the initial values which question tell us that, right? Question tell us node having its that value also, which is in the onset part. Okay. So I hope you understand these two steps. Now we take a minimum answer as 0, right? And here is the function which tell us that what is the minimum distance, what is the minimal aggregation sum, right? So here what we are taking, here the 0 is taking as a current node, right? And minus 1 as the parent node. And here the answer minimum, which tell us the aggregate minimal distance, and graph is the adjacency list, and we are passing A as a array, right? This is the array which tell us that 0 node having 0 value initially. So we have to change, we have to shuffle, right? So let's go into this part. So let's copy paste, and what does this code do? Let's understand it. Here we have the current, X is the current and F is the parent. It tells us parent. This is tell us the answer. We pass at a reference, right? Here we have the adjacency list, right? And here we have the array A, right? Let's do it. Let's do it. Let's copy this code. Now, so what this code is doing, initially we have, as I say, we have a current node as 0, right? Because it's a 0 based indexing and the parent is minus 1. And we have adjacency list, right? And have a array which tell us that initial value 0 has 0, 1 has 1, 2 has 2 and 3 has 3, right? Okay, we need these two things only. Okay, so now our adjacency list is this. Okay, we have adjacency list also this. So now first of all, what is x here? X is 0. We go into this part. Size is 1. So what's the y? Our y is f is the parent. Okay. So now our y is 1, right? Here the y is 1, which tells us that 0 is connected with 1 na. It's a current node, it's a next node of it. Okay, we have to go further. Now when we have y equal to 1, we have to check it. We have here we are writing the check position. Here we are writing the check position. Okay, for the parent part, if we are at 1, we are coming from 0 to 1, and when we reach at 1, okay, we are checking that are we checking the parent? If we are checking the parent, we have to continue, else we go further with the DFS part. Okay, we have DFS part. So now we reach at 1, right? It's not its parent because 0's parent is minus 1, right? So we are reaching to why this place, right? It means that we have to call further. We are calling further, which is one node and its parent is 0, right? Okay. Now we are coming to this point. We are coming to this point. This is 0, right? It at 0. So this is the parent. Here the y is first of all coming as 0. So 0 is matching with f, right? It's a parent. Once we are going back, but we don't want to go back, right? So here the condition is we have to do the continue part. So this is cross, we are not going into it. Now f is going to further. What is the further part? It means that 2 is also process. 2 is also 0 is process, 1 is process. Now we are going to 2 node. Now we are at this node. Okay. So it's a 2, its parent is 1, right? Now we have to process 2. This is 1 which is parent. So if condition tell us that don't go into it because it's a parent of it, we have to go to 3 part. So let's go to 3. Now we are at 3 and its parent is 2, right? Its parent is 2. Now we have to process this part, 3, 2. Okay. So when we are processing this, we see it's also parent. So continue part is going on, right? So after that, our whole adjacency list is processed, right? Whole adjacency list is processed. So in this case, you go into the if part. You go into the if part, right? You go into this part. And here the main thing came. Here the main thing came. It tells initially we have a 0 1 2 2 3 3. It tells us that we initial value is at the correct position. It's the same node and value are the same. We have to change it. So here we check. So here we check a3 right, equal to x. Yeah, a3 it's at its initial value. We have to change, right? So here we are incremented as mi equal to mi which is 0 initially. We have to add 2. Why 2? Because as you see what I tell you previous, if 0 is here, 1 is here, we have to change it. We have to swap it, right? So 0 came to here, 1 came to here, right? How many in one swap, what is the total distance? 0 is here and 0 goes to this place. How many edges are there? 1, and 1 goes to this place. How many edges are there in between? 1. So that's why we are adding 2 here in single swap. In single swap, we add as the answer plus 2, right? So this is that case. Now, if condition, we are checking this if condition f not equals to -1. Why we are adding this case? If f equal to 1, it means that f equal to -1, it tells us that it's a parent node which is not exist. We are just making -1 as a parent of 0, right? Initially, take care. So that's why, yeah, here the f is not equals to 1, here the f is 2. It means that we have to swap with the adjacent node. So let's make here, let's make here, take care. So what is x? X is this. What is f? F is this. We have to swap ax with af, right? So 3 came to this place and 2 came to this place, right? Understand? Same process. We are swapping with the adjacent and changing the array, which tell us that it's not at its initial position more, right? So this is working fine. We are going to this place and check for this. Now again we are coming to this if condition. A of x means a of 2 is at its correct position. Initially it's this point. Take care. Yeah, it's at its correct position. Take care. So we have to swap these two also. We have to swap these also, right? So we are swapping this also. Take care. One is at correct position, so we are just swapping with each other. Take care. We are swapping with each other. At the end of it, we have 3 came here, 2 came here, 1 came here, and 0 came here, right? Right? And with the same process, if you go back, ठीक है, you don't, like here it's check f of 1 is equal to 1. No, f of 1 is 0 now. So you don't go to this if condition now. Again you are going to this place, okay? So you are checking f of 0 is 0. No, it's not, right? So you are not swapping right now, right? At the end of it, are this is finished, and we are with the, we have to add 2 also because we are changing this part also, right? Okay, so we swap 2 times, so that's why we adding 2 times, so our answer is 4, right? Let's go to this part. I hope you understand this, how to find the minimal, right? Minimal is very simple. We have to just change the adjacent value, right? Adjacent value, and that adjacent value, for that change we make a array, we make this array, right? We make this array, and that help us to tell like it's changed. If it's not changed, we are adding 2 because we have to swap, we have to swap 2 numbers, so its edges is 1 plus 1, which is 2, right? So this is whole for the minimal part. Let's talk about now maximal part, right? So in this part we have the minimum, right? So now we have to go for the maximal part, right? So what's the intuition to solve the maximum? Here we are calling a DFS function, right? Here we are calling the DFS function. In this DFS function, we are again pass 0 as the current node, right? And minus 1 as the parent node, and graph as the adjacency list, and subsum as a array, right? I go to this part, like why we are using here subsum, right? So in this DFS function, same thing we are doing it. What they are doing in the subsum part, let's talk about it. So subsum simply store number of subtree nodes, right? Subsum simply store, like for example, we have 0, we have 1, we have 2, and we have 3, right? These are the 4 nodes in our example, right? So we make a subsum which tell us that, which make this, initially we have 1 nodes at each place, right? Now this function just increment, just update the subsum array, right? Subsum array, which tell us that at 0th node now, how many nodes we have in its subtree. If you count it, just do the same dry run for this case. I just tell you what subsum stores, right? Here we have 0, right? So if we talk about this, let's make it again. If I talk about what's the end result of subsum, what the subsum stores, subsum simply stores, we are at 0, right? We are at 0. How many nodes we have in the subtree of 0? 1, 2, 3, 4. It store 4 here. Simple. When we are at this place, how many nodes we have? 1, 2, 3. So we store here 3. When I am at 2 node, how many nodes we have in the starting of root 2, right? Node 2, we have 2. Similarly for this, we have 1. So in this, that DFS max just store the subsum, and it's just update the subsum, how many nodes that particular node have, right? So I hope you understand till now, right? Now the main motherboard of this question came, how we get it, like how we get it answer 8 as a maximum, right? How to solve this? Okay, let's talk about it. In initial understanding of this question, I just tell you I just tell you, just we have here 0, we have 0, so let's make its original position, like its initial position is this. Just make its farthest node as its final position of 0. Make 0 here, 3 here, 2 here, 1 here, right? Now if we count it, it's a initial, it's a final, right? It's a final part. Now just make a note of it. Just make a note of it. How many nodes, how many edges you are going through to reach final to initial to final position of it. So if we have 3 here, 0 here, we have to reach this place. It means that for 0 part, you are going through 0 to 1 node, right? Let's make it edges 1 to 2, 2 to 3, right? 3 edges. Let's talk about 1. How many edges? 1 edges, which is 1 to 2, right? For 2, we have 1 edges, which is 2 to 1, right? For 3, we have 3 edges, which is 3 to 2, 2 to 1, and 1 to 0, right? We have these many of edges. So here the count is 3, 1, 1. Here we have 3. So total is 8, right? Total is 8. Now, question arises, how to solve it? How to solve it? So to solve this part, this function is helping us. This small code helping us to solve this. How? Let's assume here we have to count this 8 edges. How we can count it? Let's suppose, let's make again this. Uh, let's make this tree again. Now we just have to make a cut and have to count how many swapping possible. How many swapping possible? Take care. We have this nodes. Let's make one cut here, one cut here, one cut here, and one cut here. Take care. We have to make four cuts, and we have to swap as many swap we are doing, right? So let's do it. So first cut is at this place, right? First cut is at this place. So if you see how many swap we can make between that cut, like in this is a cut, how many roots or say as how many nodes we have in down and up. Up has 0, up has 0 nodes, down has 4. Can we swap anything? No, not at all. So output is 0 in this case, in first cut. Let's do for second cut. Let's do for second cut. Now let's make cut here. Okay. How many ups are there in that cut? 1 up here, down here. Just count it. How many up are there? 1. So let's make it 1. How many downs are there? 3. Can we swap one number with 3? Yeah, it's possible. But can we swap 3 numbers with 1? It's not possible, right? I hope you understand. We can swap one thing with 3, any of one, right? This is 1. Let's suppose this is 1. Okay, we have this node. Okay, we have 3 nodes. We have 3 nodes. We can swap this with this. We have options, right? But can we swap these 3 with this? No, we cannot. It means that we have to take the minimum, right? So let's take, here we have 1, here we have 3. So what's the formula is, we have take 1, up is 1 node, down is 3 nodes, we have to take minimum of it and multiply by 2, right? That much edges we are going to this place. So why we are adding multiply with 2? As simple as that. We have, if we go to 0 to 1, so 1 is also go to 1 to 0, right? So that's why we are doing this. So here the answer is 2 into min of 1 and 2. Here we are swapping one number, maximum we can swap one number. So 2 into 1 is 2, right? This is first, this is second, right? Now let's talk about third cut. Third cut. So this is also over. Now the third cut is at this place. This place. Okay. So same formula. 2 into minimum of up and down. Right. Now here 2 into how much we have at the up nodes. What's the count of up nodes? We have two. How many downs are there? 2. So we can swap these two. 0, 1. We have to go beyond this cut. So 0 can go here or here. 1 can go here or here. Right? So minimum is 2 and 2, which is 2. So its number of edges in that case 4. Right? 4 we have. Let's talk about the last cut. Let's make now haircut. Okay. Fourth part. Now same formula, 2 into minimum of how many nodes we have in up part, which is 3, and in down part we have 1. How many swaps possible? 1. So in swapping we have to multiply by 2 because both are swapping, right? So 2 into minimum of 3 and 1 is, it's 1. 2 into 1 it's 2. So what's the count of it? 0 plus 2 plus 4 plus 2. So what's the count is? 8, right? What's the count is? 8. I hope you understand this intuition, how to solve the maximum part, right? How to solve the maximum part. So let's explain again a little bit of thing, right? When we are at this cut now, when we are this cut, just assume 0 is going to 1, right? As we see here is the first edge of it. 0 is going to 1. Okay, and 1 is going to 0. This is the second edges, second edge of swapping part, right? So that's why in this cut we got 2. Okay, now let's talk about this cut. Let's talk about this cut where we found 4 edges. Let's talk about this, how it is possible. So 1 to 2 is this. Okay, this is the first edge, 1 to 2. Here we got 1 to 2. Okay, here we go 2 to 1, right? Back. Here we go. Okay, 1, 2, 3. Here we go with 2 to 1, right? Right? Let's talk about the last cut. That's why we got 4 here. Okay, both are solved. Let's talk about this cut. It's 2 to 3. This is 2 to 3, and 3 to 2 is this. So that's why we got 2 here. And when we aggregate, okay, when we add all the things, we got 8. We got 8, right? I hope you understand this. Let's submit the code now and check it, right? In this case also, we have answer 0 initially, and we are add this formula which I already discussed with you. Okay, and after that we make a vector of answer and add both minimal answer and maximum answer and return it. Let's compile it and check it. Yeah, let's submit it now. Yeah, as you see, our problem is successfully, right, solved. Okay, so let's talk about its time complexity now, right? What's the time complexity is? In minimum part, in minimum, when we find the minimal part, okay, in minimal part, we just traverse this. We are just traversing this tree and going backward and just update the A array, right? A array. I think you know A array. We are just updating it. Take care. So here the complexity of minimal is big of n as we just go into the depth of it. Take care. So in maximum part, and here we are using the array A. So its space in this part is big of n, right? So in maximal part, when we find the maximal distance, here also, here also, in DFS max function, we are just update the current subsum array. Okay, we are using the subsum array in that case, so we are just updating that. So in this function, we just time complexity is big of n in that case, and in that case, and at the end, we are just traversing the loop also, n elements, right? So it tells us that its time complexity of minimal is also big of n, right? And its space complexity is, as we use the subsum array, so here the complexity space complexity is also big of n. So the overall time complexity is big of n plus big of n, right, which is equals to big of n. Take care. And space complexity is same big of n plus big of n, which is also equal to big of n or big of 2n, right? That's all. Thank you so much.